Welcome to this episode. Today, we're diving into the fascinating world of tiny machines called MEMS, microelectromechanical systems, and how a strange quantum force can cause them to stick and fail.
Yeah, it's pretty wild. These MEMS devices are like miniature machines with parts just a few micrometers in size. So small that when their surfaces get closer than about 100 nanometers, they start feeling this mysterious force called the Casimir force.
Right, and the Casimir force is kind of like an invisible quantum glue pulling those tiny parts together. It's not something you can just switch off like an electric force. It's always there when things get that close.
Exactly. And that's a big problem, because this force can cause stiction, which is when parts stick together and jam the device, making it stop working altogether.
Stiction is a nightmare for MEMS reliability. Imagine a tiny switch or sensor that suddenly locks up because its parts got glued together by this invisible force.
What's really interesting is how surface roughness plays into this. Real surfaces aren't perfectly smooth. They have tiny bumps and valleys, and that roughness actually makes the Casimir force stronger at these tiny distances.
So rough surfaces increase the chance that the device's motion becomes chaotic. Instead of moving predictably, the tiny mass on a spring inside the MEMS can start behaving unpredictably, making it impossible to tell if it will keep working or get stuck.
That's a great way to put it. Like a tiny mass on a spring oscillating near a surface. Without any external push, it either moves steadily or sticks. But when you add a periodic driving force, like a gentle push, the system can tip into chaos.
And chaos here means the motion becomes super sensitive to tiny differences in how it starts. So, two almost identical starting points can lead to very different outcomes. One where the device keeps working, and one where it sticks.
The researchers modeled this using a classical mass spring system that includes the Casimir force and surface roughness. They looked at both the undriven case, where the system is predictable, and the driven case, where chaos can appear.
They used a mathematical tool called the Melnikov method to predict when chaos would happen. What's neat is that this method shows that roughness lowers the threshold for chaos, making chaotic motion, and thus stiction, more likely.
So, from a practical standpoint, chaotic motion is bad news. It means you can't reliably predict if the device will work or fail, which is obviously a big problem for engineers designing MEMS.
That's why minimizing surface roughness is so important. Smoother surfaces reduce the risk of chaos and stiction, making these tiny devices more reliable.
And the cool thing is, this approach isn't just for Casimir forces. The same ideas could help understand other forces acting on tiny devices, especially when they operate in different environments.
To sum up, the Casimir force is a subtle quantum effect that can cause tiny mechanical parts to stick together. And surface roughness makes this problem worse by increasing chaotic behavior.
So, if you're designing MEMS, keep those surfaces as smooth as possible to avoid unpredictable sticking and ensure your device keeps running smoothly.
That's a solid takeaway. Thanks for exploring this with me today.
Thanks. It was great chatting about these tiny but tricky forces.